Hello guys, welcome back to TechDose, and in this video we will see the longest increasing subsequence and we will solve this problem in NlogN time. We will be using binary search algorithm and this is from Leetcode number 300. Now let's look at the problem statement. The problem statement is very simple. Given an integer array nums, return the length of the longest strictly increasing subsequence. So we have to use a condition that anything on the right must be greater than anything on the left of it, okay, not greater than equals to. So that is the meaning of strictly increasing. Now let's look at an example for better understanding. Let's say that we are given an array where we have elements 2, 7, 4, 6, 5 and we want to find the longest increasing subsequence. Now what can be the increasing subsequences here? You can think like 4, 6 is increasing, it is strictly increasing. You can also say 4, 5 is strictly increasing, and you can say 2, 5 is strictly increasing, yes. But if you look at it closely, you have 2, 4, 6 which is strictly increasing and this is of longest length. Why longest length? Because you cannot increase the length to get length 4, okay, there is no such subsequence. So 2, 4, 6 is one answer and there can be multiple answers, so you have 2, 4, 5 as well. You see 2, 4, 6 and 2, 4, 5 are two possible longest increasing subsequence answer. So you can return this, and in this question they are asking about the length of longest increasing subsequence, so you can return 3. Now I have already made the dynamic programming approach which is a suboptimal approach of finding the longest increasing subsequence. I'll give this link in the description below and also in the I button. You can just go ahead and watch that video. Now let's proceed and try to see the optimal approach. Now let's consider a scenario where you have seen only 4 elements in the array and there are many future elements which we have not seen. Now out of these 4 elements, you can see that strictly increasing subsequence you have 2, 6 and you have 2, 4. Okay, let's say you have an option to choose between 2, 6 and 2, 4. You also have 2, 8, but I have not taken that into consideration. So just comparing two increasing subsequences 2, 6 and 2, 4 after seeing only 4 elements. If you consider this 2, 6, you can plot a graph like this, okay, which I have plotted in the first one. And if you think about 2, 4, then this is the second plot which you can see in the bottom part. If you superimpose these two, that means taking this together, we can form this on the right hand side where the yellow line is showing you the increasing subsequence 1 and the green line is showing you the increasing subsequence 2. Now if I give you an option to choose only one of the increasing subsequence, whether you choose the yellow line or the green line, in such a way that whatever may be the future element, your chance of getting the longest increasing subsequence should be the highest. That means the increasing subsequence that you form using one of these two lines should always be the largest one. Now if you think about it carefully, then I can give you a test case. Like let's say the next items are, let's say 7, 8 and your array is ending. Now if it is 7, 8, then you can append 7, 8 in the first increasing subsequence and you can get an LIS of length 4, and you can also append 7, 8 here and you can also get a LIS of length 4, okay. And if I give you 5, 8, so let's say 7, 8 were not present but 5, 8 were present, right? Now can you append this 5 after 6? You cannot append it, okay. So there is no chance that 5 can be appended, but only 8 can be appended. So you get a longest increasing subsequence here of length 2, 6, 8, while in the second one you can append 5 after 4 and you will get 2, 4, 5, 8 which is giving you a LIS of length 4, right? So if you compare this, then the first subsequence is giving you only length 3 while the second one is giving you length 4. So why this is happening? This is happening because if you look at the gap between the two endpoints, then if anything falls in between the gap, then that can always be covered by the green line, but it can never be covered with the yellow line. Now if you think about it carefully which one to choose, then you will always go for the green line and not for the yellow line, because the longest increasing subsequence which you can get with the green line, with the green curve, which is the lower curve, will always be greater than equals to the longest increasing subsequence that you can form from the yellow line, okay. They can be equal, or if somebody has to be greater, then it will always be the green line, because the green line can also cover something in this gap, whatever is lying, right? So I gave you these two examples to showcase that. right? So this is a very important point in order to follow this algorithm. I hope you understood this. Now let's look at the algorithm rules and simply we will solve the LIS problem. Now the algorithm rules goes like this. The first point is we have to maintain a list of list for maintaining all the increasing subsequence of different lengths. Okay. Now let's say we have the items 2, 4, 6 and we will be seeing them one by one. So if I have to see 2, then I will append it and it will be a single list with the LIS of length 1. But if I see 4, then think about it. Will it be a feasible option to make another list starting with 4? And the other option is, can you just append it after 2 to get the largest length? I think you can make it out that appending 4 after 2 will increase the length of increasing subsequence, right? So if you append this 4 after 2, then we have to create a new list because the length is different, right? So I'll be creating 2, 4 here. And similarly, when you see 6, then is it feasible? Is it a good option that you append 6 entirely as a new list? Or is it a feasible option to append 6 after 2? Or is it a feasible option to append 6 after 4? So if you think about it again, then appending 6 after 4 is the best option because that is increasing the length of subsequence. So we are making our choices greedily, right? So if we append 6 after 4, then that will be made as a new list altogether because the length is different, right? So this is the meaning of first point. If you look at the second point, then it says that we have to greedily append the new element to an increasing subsequence, which will maximize the length of the increasing subsequence, and that is what we have done, right? We had multiple choices. While appending 6, I could have made a new list, or I could have appended after 2 or after 4, but appending after 4 actually gave me a list which was of longest increasing subsequence length, right? Something like that. So we will be making the choices greedily. Now looking at the third point, if two lists somehow turn out to be of the same length, then we have to discard the list with the higher end value, because as we saw here, if two increasing subsequences are of the same length, let's say 2, 6 and 2, 4, after seeing certain number of elements, then according to this proof which I had given you, the chance that the one ending at a smaller value will always see the longest increasing subsequence, and the one ending with the higher value may not be able to see the longest increasing subsequence, right? So with that logic in mind, let me just show you an example here. So let's say that I'm maintaining a list of list and I'm just seeing the first element 2. So this will be the first list. When I see 5, then where will I append? Appending after 2 makes sense. So if I append after 2, I'll make a new list altogether of length 2. Now, if I'm seeing 3, then making a list of with 3 as a single list, is not that feasible, but I can always append this after 2. And why can't I append 3 after 5? Because that is not maintaining the rule of strictly increasing subsequence, right? So I cannot append it after 5, but I can always append it after 2. If I append it after 2, then I will make a new list 2, 3. Now if you look at it, I have seen the first 3 elements. I have a list of size 1 which only contains 2. I have 2 lists of size 2. But according to the rule, we have to maintain only one list for every length. And I have 2 lists here. So which one to discard? As you can make it out that since 5 is larger than 3, so it is always optimal to discard the one with the larger end value than the smaller one, right? So I'll discard this 2, 5. When I have to see this 6 again, making a new list with 6 is not feasible. Making this go after 2 is also not that feasible, because I can always append it after 3, and that will create a new list 2, 3, 6. So if we have these many elements, then 2, 3, 6 will be the longest increasing subsequence of length 3. So I hope you got the idea, like what are we trying to do. I would like to announce about our live training programs, data structures and algorithms, which is interview dose, and system design, which is design dose. If you are looking for making a switch from service to product based, or even make a product based to product based top tier switch and aiming for your dream company, this is the best curriculum you can ever join. I'll be your mentor throughout the cohort, and I will help you clear all your doubts in the one-on-one sessions. You can know more about this by querying us on the WhatsApp number, or you can also visit our website techdose.co.in. So let's see a simple dry run. I have made the curve so that it is easier for you to imagine what we are solving. And let's maintain the list of list formulation and try to find the longest increasing subsequence. So if I see 8, I can make a list of size 1 simply. When I see 10, then I will append it after 8 and I will get a list of size 2. When I see 9, then I will append it after 8, not after 10. I cannot append it after 10, right? So I have to append it after 8. If I append it after 8, I get a longest increasing subsequence of size 2. Now there are two lists of the same size, so the one with the higher value will be discarded. So I'll be just removing it. Now let's append this 4. Where will this 4 be appended? I mean, I cannot append it after 8 or after 9. So this will have to be a new list, right? So 4 will be a new list. Now 4 and 8 are the list of size 1. So there are two lists of the same size. So the one ending at a higher value will be discarded, right? So let me just clean it up. Okay. And you just have list 4 and 8, 9. These are the two lists. Now if you look at 2, again, where to append this 2? It cannot be appended after 4, it cannot be appended after 9, so 2 has to be a new list. And if it is a new list, there are two lists of the same length, so you have to discard the one with the higher value. Now let's see for 6. For 6, we can append it after 2 and we cannot append it after 9. So let's append it after 2. So I will get 2, 6. When I get 2, 6, there are two lists of the same length, so the one with the higher end value will get discarded. Okay. Now let's look at 3. Where can we append 3? We can append 3 after 2, but we cannot append 3 after 6. That cannot happen. So I will append 3 after 2 and I will get 2, 3. Now there are two lists of the same length, so we have to discard the one with the higher end value, and so 2, 6 will go off, right? Now when you look at 5, let me change the color. So when you look at 5, then I can append it after 2 and I can also append it after 3. So it is always feasible to append it after 3 and I will get 2, 3, 5. Okay. And when you look at 9, I can append it after 2, I can append it after 3, I can append it after 5. So let's append after 5, which will give me the longest length, right? So I'll get here 9. When you look at 5, I can append it after 2, I can append it after 3, but I cannot append it after this 5 because the condition was strictly increasing. So in strictly increasing curve, you cannot have two same values, right? So I can append it after 3, and if I do that, then I will again get 2, 3, 5. Okay, and there is already a 2, 3, 5, so one of them will be discarded, and let's say the last one is discarded, right? And we are done parsing all the elements. So what do we have currently? We have 2, we have 2, 3, we have 2, 3, 5, and we have 2, 3, 5, 9. So you know that the list with the longest length will be our answer. So the LIS here is of length 4, and this is how we can solve it. Okay. Now if you look at this entire solution, how did we even solve it? So all the decision making of where a new element will go, let's say you had the new element as 4, right? Let's say the next element after 5 was 4. Now if 4 is incoming, where will it get appended to? Will it be forming a new list altogether, or will it be appended after 2 or after 3 or after 5 or after 9? It actually depends on finding the longest increasing subsequence which has the last value less than 4. Okay, you have to find the longest increasing subsequence with the last value which is less than 4. And what is that? It is 3, right? So if you maintain only the last values in some form, like let's maintain it in the form of a list, then you can easily find out the index with a value less than equals to 4. Okay, and how do you find out this? You can find out this by using the lower bound of binary search. So lower bound will give you the result of what is the first index which has a value greater than equals to 4. So in this case, if you apply lower bound on 4, then what is the first index which has a value greater than equals to 4, and that is index 2. So we can simply insert it at index 2. And why is that? Actually it cannot be inserted after 5, right? So what we do is we insert after 3. So the value will be 2, 3, 4. But now there are two lists of the same length, right? So if there are two lists of the same length, then the one with the higher value will be discarded. And so if you insert it here, then that becomes 2, 3, 4. And that is equivalent to overwriting this 5 by 4. So based on this logic, I will give you again a dry run, and where I will be maintaining a list of lists, and I will also be maintaining a single dimensional list for better understanding. So I'm taking the exact same example. When you have 8, the list of list will have just 8. And initially your single dimensional array will be empty, so you can just append 8 because if you find lower bound, it will be out of bound of the size of the LIS array, and you can just append 8 here. This is index 0. When you go to 10, then you will append 10 here, and that will make it 8 comma 10. In this case, again the lower bound search for 10 will end here, which is index 1, and this is also out of bound. Whenever you go out of bound, you will insert the element. Okay, so 10 will be inserted, and this is 1. Now when you go to 9, then simply you will append 9 after 8, and this makes it 8 comma 9, and this will be discarded. Now how do you do that in the LIS array, that is a single dimensional array? You apply binary search and find the first index which has value greater than equals to 9, and that will be index 1. So when you reach here, then you have to override this 10 value with 9, and that's it. Okay, now if you look at 4, then what to do? You have to make a new list here, right? So you will be making a list starting with 4, and then there are 2 lists of the same size, so you will be discarding it. If you are solving it in the single dimensional array, then find the first index which has value greater than equals to 4, and that will be index 0. Okay, so you override this and make it 4. Now what is our current state? I'll just stop here and write down the current state. If you look at the current state, my list of list has 4 and 8 comma 9, and I will just clean this up. Okay, we have 4 and 8 comma 9, and if you look at the array, I have 4 comma 9. Okay, so I'll also clean this up. This is index 0 and 1, and I'm cleaning this up. Fine. So I have captured these 2 endpoints of the 2 list, which are 4 and 9. Now let's go to the next point, which is 2. If you see 2, again you have to make a new list starting with 2, because you cannot append it after 4, and you just discard this 4. What happens in this single dimensional array? You have to find the first index which is greater than equals to 2. That is index 0, and you have to override this with 2 simply. When you see 6, then in the list of list you will be appending it after 2, and that makes it 2 comma 6. Now there are 2 lists of the same length, so you will so 8 comma 9 will be discarded. In the single dimensional array, you find the first element which is greater than equals to 6 by applying lower bound, and simply that will be index 1. So you have to replace this with 6 simply. Then for 3, again in the list of list you will be appending it after 2, and that makes it 2 comma 3. Now there are 2 lists of the same length, so you remove this, and that will be 2 comma 3. If you see this in the single dimensional array, find the first index which is greater than equals to 3, and that is index 1. So again you override this 6 with 3. Fine. Now let's look at the next item, which is 5. So for 5, where do you append? Can you append it after 2? Yes. Can you append it after 3? Yes. So append it after 3, and that will be 2, 3, 5. If you look at this one, the single dimensional array, we have elements 2 comma 3. So I'm again cleaning this up so that it is easier for you to follow. So the next value is 5. If you apply binary search here and try to find the first element which is greater than equals to 5, you will again see out of bound index, which is index 2. So that means you just have to append 5 to it, and that is index 2, right? Now if I again rewrite the list of list, we have 2, 2 comma 3, and 2 comma 3 comma 5. You look, these values 2, 3, 5, these are maintained in the single dimensional array as the last points. Okay, so now let me just clean this up, and you can see the rest of the values, which are 9 and 5. So when you see the 9 value, then what to do? Again you can append it after 5, and this will be 2, 3, 5, 9. If you do lower bound, again you will go to the end of the array, and simply that means you have to just append 9 to it. When you see 5, where to insert 5? Again that has to be inserted after 3. It cannot be inserted after 5, because we are talking about strictly increasing numbers, right? Strictly increasing subsequence, so we cannot append it after 5. If you append it after 3, it will be 2, 3, 5, and one of them will have to be removed. So let's remove this one only, and so it remains to be the same. In this case, you have to find the first index where the value is greater than equals to 5. That will be index 2. If you overwrite 5 with 5, it will still be 5. And we are done parsing. So this size will give you the longest increasing subsequence size, which is size 4. Okay, and in this case what we did was, for every item here, let's say there are n items, for every item we were applying binary search lower bound, right? So lower bound will actually take order of order of log n time, and we are doing it for n times, and so the time complexity will be order of n log n. and the space complexity will just be order of n because we can have all these elements in the strictly increasing order, and so the space consumed will be the same as the original array size. I hope you were able to understand this. Let's now look at the code. This is the simple code for finding the length of longest increasing subsequence. Given the nums array, I'll find how many elements are there and I'll take a LIS array, right? This is a single dimensional array. Now we will be iterating one item after another, and I'll be finding out the lower bound, that is the position where I should insert. Now there are only two conditions. The first condition is if the lower bound is denoting that I am going out of bounds, then the item is larger than even the last item. Okay, so then I will have to push back the new item, that means append at the end. Otherwise, if it is pointing out to some inner item, that means some item of the array, then you just have to overwrite it. And these are the only two conditions. So if you have understood the theory algorithm, then this is extremely simple to code. Okay, I hope you were able to understand it. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.